By seeing the molecule itself, you can analyze which is Lewis acid and which is Lewis base. H plus into OH minus, you know 1 into 10 to the power of minus 14. Taking logarithm on both sides, log H plus log OH minus minus 14 log 10. Root of Ka1 by Ka2 will happen. This C will get cancelled. This is the formula to use relative strength of acids. Hello everyone, this is Harshita Bhavasar from Vidhyaashram, PU College, Temple of Excellence. Today I am going to start session 6 from the chapter Chemical Equilibrium. In the last session we have discussed about acid bases and salts, hydronium and hydroxyl ions, and how the acidic properties will behave in the periodic trends. We have seen these three concepts in the previous session. In today's session, we will discuss about Lewis concept, limitation of Lewis concept, ionic product of water, and still some of the relative concepts of acids and bases, relative strengths of acids and bases also we will see in the today's session. What do you mean by Lewis concept? According to Lewis concept, an acid is an electron pair acceptor and base is a electron pair donor. Okay, according to Lewis concept, an acid is electron pair acceptor. Electron pair means 2 electron should be or acid should be accepted. Base means electron pair donor. 2 electrons should be donated. Acid is an electron pair acceptor or an electrophile. Usually electrophile will be represented by plus or E plus. So acid is an electrophile and base is an electron pair donor or nucleophile. Okay. Example, in ammonia, nitrogen atom has a completed octet with 1 lone pair. It can act as a base by donating the lone pair. BF3 has 6 electron arrangement and needs 2 more electrons to complete its octet. BF3 can behave as an acid. Thus, when NH3 and BF3 will combine, see here, base and acid. Here due to this lone pair is present, this NH3 will act as base. Here it needs 2 electrons to complete its octet. So this will act as acid. Okay. See here NH3, 1 hydrogen will be accepted with plus sign. Lewis concept is more general than Lowry-Bronsted concept. According to Lewis concept, the following species can act as Lewis acids. After Lowry-Bronsted concept came, Lewis concept has been introduced. More than Lowry-Bronsted concept, Lewis concept was more general, and according to Lewis concept, the following species can act as Lewis acids. What are those following concepts? Molecules in which the central atom has incomplete octet. The central atom should have incomplete octet. See here, aluminium, incomplete octet, beryllium also incomplete octet, here boron, here also boron. The central atom should have incomplete octet, means it should not have the complete octet configuration. Those will act as Lewis acids. Next, simple cations. All cations Lewis acids because of their positive charges. See, Na plus, K plus, calcium 2 plus have least tendency to accept electrons, while cations like H plus, Ag plus have a greater tendency to accept electron and act as Lewis acids. Usually the atoms which have positive charges will act as Lewis acid. In that also sodium, potassium, calcium are less tendency to accept electrons, but hydrogen and silver have more tendency to accept electrons, so it will be acting as Lewis acids. Next, molecules in which the central atom has vacant d orbitals. Example, halides like SiX4, germanium X4, titanium chloride, here also tetra chloride, and tin tetra halide. Like this, halides with or metals with vacant d orbitals will act as Lewis acids, and they can accommodate pairs of electrons in their vacant d orbitals. Usually molecules should have vacant d orbital, those will be considered as Lewis acids, and what all the electron pair which will accept by the others, it will be placed in vacant d orbitals. Okay. Next, molecules having multiple bonds between atoms of different electronegativity, example CO2, SO2, SO3, etc. in presence of a Lewis base, at electron pair will be shifting towards the more electronegative atom. The less electronegative atom becomes electron accepting and gets connected to the base. In molecules having multiple bonds between two atoms having major or different electronegativity, when electronegativity is more, it will donate the electrons. When electronegativity is less, then it will electron starts accepting. Okay, it shows acidic nature. See here, acid, it accepts the electron. Next, base, here bicarbonate will form. Here also SO2, here also bicarbonate will form. The following types of compounds behave as Lewis bases. We have seen what all the compounds or what are the molecules will act as Lewis acids. Now, what all the types of compounds or molecules will act as Lewis base. Neutral species with at least one lone pair of electrons. See here, lone pair of electrons are present on it, means it will be considered as Lewis bases. In all the species you can observe, lone pair of electrons are present. Negatively charged species are anions. Here negatively charged species will also considered as Lewis bases. Ligands in coordinated complex. What all the ligands will see in coordination compound, those will be also considered as Lewis bases. One lone pair of electrons should be present, and negatively charged species also ligands in coordination compounds. Why this? We have to understand, means by seeing the molecule itself you can analyze which is Lewis acid and which is Lewis base. Then you can proceed the reaction with further details. Next, limitation of Lewis concept. The strength of Lewis acid or base depends on the type of reaction. Hence, it is not possible to arrange them in any order of the relative strength. The strength of Lewis acid or base depends on the type of reaction. On the basis of type of reaction, the strength of Lewis acid and Lewis base will be considered. Hence, it is not possible to arrange them in any order. We have seen many Lewis acid, we have seen many Lewis bases. We cannot arrange in any order among those molecules. So, you cannot understand the strength of Lewis acid and Lewis base. The choice of use of these concepts depend on the nature of the reaction being studied. But for most simple purposes, Arrhenius concept is quite satisfactory as it is simple and explains the relative strengths of acids and bases, neutralization and salt hydrolysis. For simple reactions, Arrhenius concept can be taken into the help, but also to understand major nature or major relative strength, this Lewis concept is failed or it cannot be applied. For that, neutralization and salt hydrolysis can be done. Next, ionic product of water. Even very pure water conducts electricity to a small extent. This is because the following ionic equilibrium exists in it. Usually we will tell impurities in water, water in which impurities are present that will conduct electricity more fastly than pure water or purified water. But here they are telling due to the ionic equilibrium, very pure water also conduct electricity in a small matter. See, even very pure water conducts electricity to a small extent. This is because the following ionic equilibrium exists in it. In water it gets ionized. Here H3O plus and OH minus will form. K is equilibrium constant, you know. This is product by reactant. Water is only feebly ionized and hence H2O may be taken as a constant at 1 dm cube equal to 1000 gram. Number of moles of water 1000 by 18. 18 how it come? H2O 2 into 2 plus 16. So 18 equal to 55.6 molar. Therefore, equilibrium constant of that reactant will become equal to product. Reactants will become to product. So Kw is equal to H3O plus into OH minus. That concentration of H3O plus into concentration of OH minus. where Kw is the ionic product of water. H3O plus is hydronium ion. It may be thought of as hydrated H plus ion. Therefore, Kw equal to concentration of H plus into concentration of OH minus. Ionic product of water is a constant at constant temperature. Here, what they are telling, very pure water can be conduct electricity by the purified water. How they have shown, 2 molecules of water and it is getting ionized into H3O plus into OH minus, and they have calculated for the molarity and they got 55.8, and they are telling the ionic product of water will be equal to concentration of H plus and concentration of OH minus. So, this you can tell water is a neutral also. Its value at 25 degrees Celsius is 1.0 into 10 to the power of minus 14. At 0 degrees Celsius, Kw equal to 1.1 into 10 to the power of minus 15. At 100 degrees Celsius, Kw equal to 5.5 into 10 to the power of minus 13. Pure water contains equal quantities of H plus and OH minus. Okay. See all the values. At 25 degree, 1.0. At 0 degree, 3.31 into 10 to the power of minus 8. At 100 degrees, 7.42 into 10 to the power of minus 7 mole per dm cube. If some acid is added to water at 25 degrees Celsius, concentration of H plus becomes greater than 10 to the power minus 7 molar and corresponding OH minus concentration is reduced to less than 10 to the power of minus 7 molar. On the other hand, if some base is added, OH minus will be greater than 10 to the power of minus 7, and so H plus ion will be lesser than 10 to the power of minus 7 molar. Thus, neutral acidic basic can be identified. What they are telling, when water is in the equal concentration of H plus and OH minus ions, then if you add acid to that water, the acidity will increase more than 10 to the power of minus 7. Or if you add base to that same water, the basicity will be greater than the acidic nature. By that, basic acidity will be more than 10 to the power of minus 7. See here, neutral 10 to the power of minus 7 molar and 10 to the power of minus 7 molar. Both concentration are equal. Acidic means greater than 10 to the power of minus 7. The basicity will be less. Here, basic will be 10 to the power of minus 7. Here will be less. Concentration of H plus or concentration of OH minus in acids and bases. In the case of strong acid, concentration of H plus is equal to the normality of the acids as it is completely ionized. Concentration of H plus equal to normality of the acid equal to molarity into basicity. Okay, this is the formula. Hence, OH minus will be equal to 1 into 10 to the power of minus 14 by N at 25 degrees Celsius, where N is normality. Okay. In case of a strong base, OH minus equal to normality of the base equal to molarity into acidity. This formula you have to know. Here one formula and here one formula. Normality of acid, molarity into basicity. Normality of the base, molarity into acidity. Same thing, 1 into 10 to the power of minus 14 by N. If the acid or base is weak, Oswald's dilution law is used to calculate H plus or OH minus or concentration of the acid in aqueous solution. For weak acid, concentration of H plus equal to C alpha, but alpha is equal to root of Ka by C. Therefore, H plus equal to KaC will become. This is Oswald's dilution law will be implemented to the above formula, where Ka is the dissociation constant at given temperature and C is the concentration of the acid. For weak base, same here, C alpha equal to root Ka into C, that is Kb. Okay. This is how the weak acids and weak bases will be calculated by using Oswald's dilution law. Next, the pH scale or Sorensen's pH scale. To avoid expressing H plus as negative power of 10, Sorensen proposed pH scale. pH of a solution is defined as the negative logarithm of to the base 10 of H plus concentration Mathematically, pH equal to minus log 10 into concentration of H plus equal to log 10 1 by concentration of H plus. Okay. So, pOH of a solution is defined as the negative logarithm to the base 10 of OH minus concentration. See, minus log 10 into OH minus equal to log 10 into 1 by OH minus. This is for pOH or basicity. In aqueous medium, H plus and OH minus equal to Kw is equal to 1.0 into 10 to the power of minus 14. Hence, at 25 degree, pH plus pOH equal to 14. Okay. See here, pH scale neutral 7 at both the ranges. Acidic means less than 7. Basic means more than 7. Okay. See, this is overall pH scale. 0 to 14 will be the range. Okay. 1, 10 to the power minus 1, minus 2, 2, 10 to the power of minus 14. From 7 to 14 increasing in basic strength. From 0 to 7 increasing in acidic strength. Okay. From here to 0 increasing in acidity. From 7 to 14 increasing in basicity. At the range of 7 it will be neutral. Means it can act as acid or it can act as base. It is found that every increase of H plus concentration by 10 to the power of x, the pH of a solution decreases by 10 units and decreases in concentration by 10 to the power of x, the pH increases by x units. To show that pH plus pOH equal to 14, this derivation is very much important for your examination purpose. See here, H plus into OH minus, you know 1 into 10 to the power of minus 14. Taking logarithm on both sides, log H plus log OH minus 14 log 10. Multiplying throughout by negative sign, what will happen? Minus log H plus minus log OH minus equal to minus into minus here 14 will become, or pH plus pOH will become 14. Very simple 3 steps, but you should know how it has been proved. Measurement of pH. Measurement of pH of a solution is very essential. pH values will plays very important role in biological and cosmetic applications. It can be determined by various methods. pH you should know in all the areas or what all the applications you should know. Usually biological and cosmetic applications will show a variety of range. Okay. By using pH paper, the pH range 1 to 14 can be determined with an accuracy of 0.5. For greater accuracy, pH meter is used which measure pH dependent electrical potential or of a test solution with the 0.001 precision. How to detect the pH means you have pH strips. There will be indication on its box. By using those strips you can analyze at what range pH has been proved. But there is a chance of accuracy of 0.5. To get accurate value, you can use pH meter also. Their precision value will be 0.001 precision value will be present. By these two methods, pH can be calculated. Next, name of the fluid and name of pH. Okay. Saturated solution of NaOH approximately 15. Means 0.1 molarity of sodium hydroxide solution will be 13. Lime water 10.5, milk of magnesia 10, egg white 7.8 or sea water, human blood 7.4, milk 6.8, human saliva 6.4, black coffee 5, tomato juice 4.2, soft drinks and vinegar 3, lemon juice 2.2, gastric juice 1.2, 1 molar HCl solution 0, concentrated HCl 1.0. This is some of the solutions with its pH you should know. This is some of the examples. Next, ionization of weak acids and weak bases. How that weak acid and weak bases can be ionized? You know that already it can be ionized partially, but how? Let Ha be the weak acid, Ha equal to H plus A minus, product by reactant. Ka is called dissociation constant of weak acid. H plus A minus and Ha are the equilibrium concentration of H plus A minus and unionized Ha respectively. If C is the concentration of acid in mole per liter, then alpha is the degree of dissociation. Okay. For weak acids and weak bases, Ka equal to alpha square C by 1 minus alpha. This is the formula you have to know. When alpha is small, K equal to alpha square C. Here 1 minus alpha will be neglected. The degree of dissociation alpha equal to root of Ka by C. For base, let BOH be the weak base. BOH equal to B plus OH minus equilibrium constant. You know how to write. Kb equal to alpha square C by 1 minus alpha. Kb is the dissociation constant of weak base and alpha is the degree of dissociation at a concentration C. For acid and bases, same formula, just only you have to change the acids or base as a or B respectively. Next, dissociation of weak polybasic acids. Polybasic acids means H2S, carbonic acid, phosphoric acid, etc. More than one replaceable hydrogen atom like H2SO4, anything. Okay. Each stage is associated with its own dissociation constant. For example, the weak acid H2S dissociated as H2S gives rise to HS minus plus H plus. First K1 this is. Next HS will be H plus plus H2 minus. This is second level. 2 times dissociation will takes place. Okay, it is depending on the number of replaceable hydrogen atoms. So what will happen? K1 and K2 are the known as primary and secondary dissociation constants. H2S equal to K1 equal to 1 into 10 to the power of minus 8 and K2 will be 1 into 10 to the power of minus 13. The extent of dissociation decreases markedly from primary to secondary stage. The overall dissociation constant for hydrogen sulfide is K equal to K1 into K2. This is the overall for H2S. Next, relative strength of acid. Strength of an acid depends only on the extent of its dissociation to give H plus ion, not on its concentration. In the case of a weak acid, H plus ion concentration is low. At higher concentration and upon dilution, degree of ionization increases, and finally, the infinite dilution, the acid becomes completely ionized. Thus, at infinite dilution, all acids have equal strength. Usually, we have to understand the acids will become more strength when it is giving more H plus ions, not based on its concentration. If it is keep on diluting at one constant, it doesn't get diluted. Okay, that time acids will be having equal strength. But at all other concentrations of equimolar solution of different acids, the degree of dissociation may be different and H plus ion concentration may be different. But at all the concentration of equimolar solutions, you have taken so many acids in equimolar solution, that time concentration will be different and degree of dissociation will be different. Thus, to measure the relative strength to acids, the measurement of H plus ion concentration in equimolar solution is found out by various methods. One of the methods is described below. How? The from dissociation constant, let Ka1 be the constant of acid 1 or alpha 1 be the degree of dissociation at a concentration C. And another one Ka2 and alpha 2. What they have done? By using Oswald's law of dilution, alpha 1 equal to root of Ka1 by C and alpha 2 equal to root of Ka2 by C by strength of acid 1 divided by strength of acid 2. Then what will happen? Alpha 1 by alpha 2. Root of Ka1 by Ka2 will happen. This C will get cancelled. This is the formula to use relative strength of acids if two acids are there. According to Arrhenius' theory, the strength of a base depends on its ability to ionize, give OH minus ions. According to Arrhenius' concept, which solution will give more OH minus ions, which will liberate more OH minus ion, that will be considered as strong base. Hence, the same method described for weak acids can be adopted to find relative strength of bases. Same values we have taken. pK values, the strength of weak acid or weak base can also be expressed in terms of pK values. For weak acid, pK equal to minus log A. For weak base, pKb equal to minus log Kb. The strength of an acid or a base is inversely proportional to its pK values. Okay, pK value will be inversely proportional to the strength of acid or strength of base. Smaller the pK, stronger the acid. If the pK value is small, then stronger will be the acid. Example, pK of formic acid 3.752 and pK of CH3COOH 4.7447. Hence, formic acid is stronger than acetic acid. This value is pK value. This is lesser than this, but it is stronger than this. Similarly, pKw equal to minus log Kw and pH of water will be pKw by 2. Relation between Ka and Kb. Ka and Kb represent the strength of acid and base respectively. In case of conjugate acid and base pair, they are related in a simple manner so that if one is known can be deduced considering the examples of NH4 plus and NH3. Okay. See here, in NH3 in aqueous solution or aqueous medium, in water NH4 plus OH minus. If you take the equilibrium constant, product by reactant, what will happen? NH4 plus in water medium, H3O plus and ammonia. After taking same equilibrium constant, 2H2O gives H3O plus and OH minus. Net reaction Kw equal to H3O plus into OH minus, where Ka represents the strength of NH4 plus as an acid and Kb represents the strength of ammonia as base. Usually we know this is a base and this is a acid. That is how we have proved here. Okay. Ka into Kb, okay, H3O into NH3 by ammonia. This overall calculations will show H3O plus into OH minus will give Kw. Now what we have understood, Kw equal to Ka into Kb. If both sides multiply with minus log, what will happen? Minus log Kw minus log Ka minus log Kb. So pKw equal to pKa plus pKb. This formula is also very much important for your numericals as well as your competitive examinations. Common ion effect. Suppose that a strong electrolyte and a weak electrolyte dissociate in the same medium to produce an ion in common to both the substances. The strong electrolyte has a tendency to further suppress the dissociation of the weak electrolyte. In one medium, if strong electrolyte and weak electrolyte are present and they are liberating their action, then the strong electrolyte will suppress the action of weak electrolyte. That is called common ion effect. The decrease in the dissociation of the weak electrolyte by addition of strong electrolyte containing common ion is called common ion effect. This can be understood from the effect of sodium acetate, a strong electrolyte, on the dissociation of acetic acid, which is a weak electrolyte. In CH3COOH gives CH3COO minus plus H plus. This is Ka, overall equilibrium constant. Okay. CH3COO Na, which gives CH3COO minus into plus Na plus. The effect of adding CH3COO minus in the form of acetate is to increase that CH3COO minus. The extent of forward reaction, that is the dissociation of the acid, decreases, illustrating the effect of the common ion. This effect has an important application. It is possible to modify the concentration of one of the ions of a weak electrolyte by modifying the concentration of the other ion. Okay, this is how the common ion effect will be working. By the strong electrolyte will suppress the action of weak electrolyte in the same medium. This is about the relation between Ka and Kb and all the relative strength of acids and bases also we have seen. In the next session, we will discuss about buffer solutions, pH of buffer, that is Henderson's equation, and buffer capacity. Overall, what is buffer solution, how it will act, What is its application? We'll see in the next session. I hope you have understood completely whatever I have taught today. We'll meet in the next session. Thank you.